Good morning. A very warm welcome to all of you for this special PRL Colloquium. On this day, we are joined by Professor Mohit Randeria from the Ohio State University. And I take this opportunity to welcome Professor Randeria as well. And he's joining us pretty late in the evening, so I really appreciate it. And on behalf of PRL, I would like to thank him for kindly accepting our invitation and agreeing to speak to us on this interesting and very exciting topic, which we will be hearing in a few moments from now. To introduce the speaker formally, I will now request my colleague, Dr. Navinder Singh, who had a lot of interactions with Professor Randeria, to kindly do the honors. Please introduce the speaker and conduct the proceedings. Professor Navinder.
Yeah, thank you, Professor Palam. So, good morning, everyone, and good night to you, Professor Mohit. It's really a great pleasure and honor to introduce today's colloquium speaker, Professor Mohit Randeria. Professor Mohit is a leading figure in the field of unconventional superconductivity. The renormalized mean field theory and the quantum Monte Carlo RVV theory are benchmarks in the field of unconventional superconductivity. He has several very important contributions in the field of strongly correlated systems. So let me briefly go through Professor Mohit's very bright academic trajectory. So he obtained his BTech in electrical engineering at IIT Delhi and MS at California Institute of Technology, shortly called Caltech. Then he obtained his PhD in theoretical condensed matter physics from Cornell University under the guidance of Professor J.P. Sethna. Professor J.P. Sethna is one of the pioneers of the strongly correlated systems. After postdoctoral research with the Nobel laureate Professor Anthony Leggett at the University of Illinois at Urbana-Champaign, he taught at Stony Brook, and he has been a staff member of Argonne National Labs. He was on the faculty of TFR, Mumbai, from 1995 to 2004. He has been a visiting professor at several prominent places, namely at Urbana-Champaign, 2003 to 2004, at Berkeley, 2015, at MIT, 2016. He has been awarded the B.M. Birla Prize in 1997, Swaran Jayanti Fellowship of DST in 1998, Shanti Swarup Bhatnagar Prize in 2002, ICTP Prize in 2002, Distinguished Alumni Award of IIT Delhi in 2007, and the Fellowship of the American Physical Society in 2008. So with this introduction, I would like to request to Professor Mohit to start his presentation. And before that, I would like to add a comment here that this is regarding questions. If you have any questions, please type your question in the comments column. So I will take them one by one. And Professor Mohit told me yesterday that there is no problem even if there is a question during the proceeding itself, and you can have your question and I will pass over to him. And also you can ask questions at the end of the session. Okay. So with this, I would like to hand over to Professor Mohit for today's colloquium. Thank you very much.
Okay. Thank you very much. Can everyone see my screen, my pointer moving? And can everyone hear me? Maybe Navinder, you can give me a thumbs up if everything's okay.
Yes, we can.
Okay, thank you very much. So I would like to thank Professor Palam Raju and Navinder both for giving me this opportunity to present this online colloquium at PRL in Ahmedabad. It's actually particularly important for me to be presenting this work in Ahmedabad because I have a long association with that city. My mother's family has lived there for generations. And after my father's retirement, my parents also lived there for almost 3 decades or more. And so until 5 years ago, and when my father passed away, Ahmedabad was home to me. So I'm particularly excited at this opportunity to deliver this talk at PRL. So today, I want to talk about some recent work that we have done on limits on the superconducting transition temperature. My research group these days is working a lot in problems away from superconductivity, particularly in magnetism and topological states of matter. And those of you who want to see other work going on in my group can go to my group website. So let's start the story today. First, since this is a colloquium, I'll begin at a very general level. So I'll start with telling you what is superconductivity and why should you care about it, especially if you don't work in the field. Okay, so very quickly, superconductivity is a state of matter where the resistance actually drops to identically zero or lower than anything that can be measured by any standard measurement technique. So if it's below the noise floor, you call it zero. And theoretically, now we know that it's actually zero. And this is a phenomena that happens below a certain temperature, which is called the transition temperature or critical temperature T sub C. So this was first seen in the lab of Carmelin Owens in the year 1911, for which he received the Nobel Prize within 2 years. And this is actually his original data on mercury, which has a rather low transition temperature of 4.2 Kelvin. Then a couple of decades later, it was recognized by Meissner and Oschenfeld that not only is the resistance in the superconducting state zero, but the magnetic field inside a superconductor is also zero. So if you think of this as the field lines going through the superconducting blob, then when you cool below Tc, the field lines are expelled so that at least a sufficiently small field is completely expelled. And this is called the Meissner effect. And it took many years to understand this mystery. In fact, there was huge attempts over more than 4 decades to understand this unusual state of matter. And finally, the problem was cracked by Bardeen, Cooper, and Schrieffer. And this is the celebrated BCS theory of superconductivity. And they showed how superconductivity arose as a macroscopic manifestation of quantum coherence, for which they too won a Nobel Prize. In fact, this was Bardeen's second Nobel Prize. He's the only person to have won 2 Nobel Prizes in physics. Marie Curie won one in physics and the other in chemistry. His first Nobel Prize was for the invention of semiconductors. So, although this may seem like a very important piece of condensed matter physics or solid state physics, what I want to tell you is that this field of superconductivity has had tremendous impact on diverse fields of science. So for instance, Nambu himself worked on superconductivity in the early days and then took the idea of a spontaneous symmetry breaking which happened dynamically. And actually, he took this idea from superconductivity to high energy physics. The idea of how a Nambu-Goldstone boson in a neutral superconductor would actually get gapped out in the presence of a gauge field, and this is the basic idea of the so-called Anderson-Higgs mechanism, led to the work of Higgs, Englert, Braut, and many others, for which Higgs and Englert also won the Nobel Prize. The Ginzburg-Landau theory of superconductivity, due to Vitali Ginzburg and Lev Landau as early as 1950, was in a sense the very first effective field theory ever written down. And of course, the work of Ginzburg and Landau had a profound influence on the way in which Wilson constructed effective field theories, and that led to the development of the renormalization group by Ken Wilson. Finally, the idea that topological defects in some ordered state could have a dramatic effect also led to 2 other Nobel Prizes. The first was Abrikosov, who was a student of Landau, who discovered vortices or predicted them theoretically, and so for which Abrikosov won the Nobel Prize. And then the more recent work of Kostlitz and Thouless, which we will come back to, about how topological defects can drive phase transitions. Also, very soon after BCS, pairing in nuclei, even odd effects were understood. People now believe that there's superconductivity in neutron stars, neutral superfluidity of paired neutrons, but also superconductivity of paired protons. And in fact, this is responsible for, say, glitches in pulsars. There are strong beliefs, although no clear experiments, of color superconductivity in QCD. And if you want to see a sort of rather inspiring essay on BCS as foundation and inspiration, there is a very nice little article by Frank Wilczek. Now, when I say that, these are impacts of superconductivity on other fields, I'm not saying that in some loose sense. If you look at Higgs's famous paper for which he won the Nobel Prize, he says in the first paragraph, the phenomena is just the relativistic analog of the plasmon phenomena to which Phil Anderson has drawn attention, that the scalar zero mass excitation of a superconducting neutral Fermi gas becomes the longitudinal plasmon mode of a finite mass when the gas is charged. So there it is, a direct impact of the theory of superconductivity in this case on the development of the Higgs phenomena. And of course, to observe the Higgs phenomena and to do many particle physics experiments, they use superconducting magnets at CERN. Okay, so these are niobium titanium wires which are maintained well below their transition temperature of 10 Kelvin. So this is one of the very beautiful things about condensed matter physics, that not only does it lead to fundamental deep insights into nature, but also leads to many applications. Now here I've shown you an application which then again leads to new fundamental insights into nature in experimental physics. But here is an application that a lot of us care about, whether we care about Higgs or not. Namely, every MRI machine has a superconducting magnet in it. Okay, and more recently, it's the superconducting platforms which have led to the most important progress in the experimental implementation of quantum computing. So here I show you two articles in New York Times a couple of years ago about the breakthroughs due to superconducting qubits. And it's very important to realize that Abrikosov's work on vortices in type 2 superconductors lies at the basis of the magnets that are made out of superconductors. And Josephson's work on Josephson effects led to the idea of Josephson junctions, which underlie the superconducting qubits. So there is a very strong connection, sometimes spanning many decades, between fundamental discoveries such as Abrikosov's and Josephson's and their applications on a large scale. So that brings us to the question of superconductors and their transition temperatures. Okay, so the first thing I want to tell you is that superconductivity is not something which is seen in only a few systems. So if you look at the periodic table, I mean, almost half the elements actually have a superconducting ground states. These are the ones which have been colored in blue, and green are only under high pressure. Okay, now that's just elements. And then there is a vast variety of alloys and compounds with very complicated crystal structures. Okay, and the high temperature superconductors, the cuprate materials are shown in the middle, which are all superconducting. Now, this is an old periodic table where carbon was shown to be non-superconducting, but recently it has been shown that if you take two layers of graphene and twist them relative to each other close to a certain magic angle, that too becomes superconducting. So there's an abundance of superconductivity in nature. Now let's look at superconducting transition temperatures, because that's the focus of the talk today. So here I'm showing you a plot of the transition temperature versus time. The first superconductor is mercury, and now this is where my PhD happens, 1987. So I stopped there, okay? And then comes the copper age of superconductivity, boom. These are the high temperature copper oxides whose transition temperatures are still actually the highest transition temperatures known at ambient pressure, close to about 150 or 160 Kelvin. Okay, and then comes the iron age of the iron-based superconductors, which also actually go up to about 100 Kelvin. And here you can see that there's hydrogen sulfide at high pressures, 150 GPa, which is at 200 Kelvin. And then very recently, just last year in Nature, it was reported that the highest transition temperature seen in a laboratory is 15 Celsius. Okay, so it's a room temperature superconductor. The only downside is it's at a humongous pressure of 260 gigapascals, which is roughly 75% of the pressure at the core of the Earth. Okay, so it's under only very high pressures that this is seen. And this is in carbonaceous sulfur hydride. Now, while we are talking about superconductivity in extreme conditions rather than ordinary laboratory conditions, an extreme example is that the estimated TC for paired superfluidity in neutron stars is like 10 to the 9 Kelvin. Of course, all the scales there are humongous. You know, instead of having a Fermi energy, which is, say, of order a volt or 10 volts, it's actually 10 to 100 mega electron volts, okay? And the temperature there is the room temperature of a neutron star is also 10 to the 8 Kelvin. So anyway, this seems to suggest that TCs can become extremely high, and one would like to understand, of course, one is most interested in understanding how high TC can be in a lab, but even more importantly, one should ask what determines the superconducting transition temperature. So I'll break the answer into two parts, the BCS answer, which is the conventional one, and beyond BCS. So the BCS answer is the following, that if you look at a metal, then you fill up all the states inside a Fermi sphere of radius kf or h bar kf. Okay, so all these states are filled, all the states outside are empty, and kf is the Fermi wave vector. Because we have a quadratic dispersion, this also defines a Fermi energy, h bar squared kf squared over 2m. And now what BCS said was that if you have a weak attraction between the electrons, and in the original BCS theory, they were thinking that the attraction would come from the interaction of the electrons with the lattice or electron-phonon interactions. But the origin of the attraction is not so important. Of whatever origin, if there is a weak attraction, then this Fermi surface, which is a locus of gapless excitations, because you can take a fermion from inside and put it just outside the Fermi surface with very low energies. So there are lots of low energy excitations living all along the surface of radius kf. That becomes unstable, because what happens is that this weak attraction leads to pairing, okay? And the pair binding energy delta is responsible for opening up an energy gap in a superconductor. At the same time as you get pairing at that same transition temperature, you also get condensation. And that condensation of pairs, meaning a macroscopic occupation of the zero center of mass momentum state for pairs, leads to all the super properties, superconductivity. So you can see from this picture, since you have a very weak attraction, the binding energy is very small. So delta in the energy scale is much, much smaller than the Fermi energy scale. So TC, the transition temperature at which superconductivity is destroyed and you go back to a normal metal, scales with delta. There is some standard formula, 2 delta over kBTC is 3.5. The number is not important, but the larger the energy gap, the larger the TC. The two are proportional to each other. And both of these scales are tiny, exponentially small compared to epsilon Fermi. In typical superconductors, TC is of order Kelvin, 10 Kelvin, okay? Whereas the Fermi energy is of order volts or 10 volts. And as you know, that's a huge difference of temperature scales. So in the BCS theory, the answer is TC is controlled by the pairing gap. The more strongly bound the electrons in a Cooper pair, the higher the transition temperature. And there are some standard formulas which tell you how TC and delta scale with the Debye energy, because the phonons are involved. With the, it's an essential singularity exponential -1 over g. This is a celebrated result of BCS, where the dimensionless coupling constant involves some density of states and attraction. It's not very important what it is, but it's just that since g is very, very small, this number is tiny compared to all other energy scales in a solid. And there are more detailed theories of superconductivity due to Migdal, Eliashberg, and others, which treat the electron-phonon interaction in much more detail. Okay, they give you answers which are quantitatively different from BCS theory, but qualitatively similar. TC still scales with the gap or the value of the energy gap with zero temperature. But the only thing I really want you to note from it, if you're not an expert, is that there's a sensitive dependence on the mechanism, the nature and strength of the attraction. So the point is that if you look at a formula like this, then the experimentalist feels wonderful. If I can somehow make a stronger attraction, or if I can have a larger density of states, then basically I'll enhance G. And if I enhance G, I'll get a higher TC. So this seems that by choosing a suitable material having more attraction, larger density of states, there's no limit to TC. Okay, is this true? Or is this actually a misleading statement? And there, in fact, are limits to the growth of TC. So this is not a question you can settle by theory. So let's look at experiment. What does experiment tell us? So here is a recent plot from the recent Nature paper of the MIT group of Harillo Herrero, where they actually discovered superconductivity in magic angle twisted bilayer graphene. But what they did in this plot is they took, I don't know, some more than 24 superconductors. And on the vertical axis, they plotted their transition temperatures and note a logarithmic scale. And on the horizontal axis, they plotted the Fermi temperature, or the Fermi energy divided by Kb. Again, note the logarithmic scale. Now, of course, as any experimentalist will tell you, you can hide a lot of sins in a log-log plot. And secondly, you could also get into lots of discussions of how do you determine the Fermi temperature of some strongly correlated material or a multi-band system, whereas the TC is a measured quantity. But I think none of those points are particularly relevant because there are trends that are just staring at you in this picture. It's qualitative physics. If you look at the BCS superconductors, zinc, aluminum, tin, niobium, they are out here. But all the unconventional or the more recently discovered superconductors seem to be going towards the left and upwards. And then there seems to be a line which none of them cross. Okay, so here all these BISCO, YBCO, LASCO, these are all the high temperature superconductors. Twisted bilayer graphene, ultra cold atoms, iron selenide, etc., etc. So one question that arises is there a limit on TC? Or is there a ceiling, as it were, on TC divided by epsilon Fermi? So that there is some line, which I've just drawn as a dashed line, artist conception, and that no matter what you do, nature will not allow you to discover a superconducting state in the region that I have marked with a question mark. Okay, is that true or not true? Now, the fact that the systems that come close to this line are magic angle twisted bilayer graphene, two systems of ultra cold atoms, which, by the way, their TC and EFs have been scaled by huge factors of 10 to the 8 or 10 to the 9. So they're way down here, but nevertheless, they are along the same line. And iron selenide on STO. I mean, these are such different systems, some solid state, some ultra cold Fermi gases, that the bound cannot depend sensitively on mechanism if, in fact, there is such a bound, because that's what BCS tells you. So that says, okay, let's look beyond BCS and ask, can we understand something there? So the superconducting order parameter is a complex number. And why is there an order parameter? Because there is a phase transition at which you get a macroscopic number of pairs in a single quantum state. And very roughly speaking, this order parameter says something about this single quantum state. And because it's a quantum wave function, it's a complex number. More technically, there's a broken U1 symmetry and a certain expectation value. But in any case, the actual superconducting order parameter is an amplitude and a phase. The amplitude is the magnitude of the order parameter, and actually, when written in correct units, it's just the energy gap that arises from pairing. And this leads to all the experimental things that you can probe in thermodynamics and spectroscopy, telling you that there's an energy gap. But there is also the phase, which is often not talked about in elementary classes. But in fact, it is the phase which is responsible for all the superfluid properties: motion of charge without dissipation, expulsion of the magnetic field, and the Josephson effect. So let's ask how this is relevant. So suppose I have an order parameter with an amplitude and a phase, which is locally well defined. Then long-range order could be destroyed in two ways. Either you just suppress the amplitude everywhere and make it go to zero, then of course there's no long-range order. This is the BCS route. The TC just scales like the energy gap, which actually is the amplitude of the order parameter. But what about the phase? Could it do something? So another option is that you could randomize the phase. This is the way you think about very often disordering a magnet, which is a vector, and then the length of the vector doesn't really change locally, but the directions can become randomized. And there is some history of thinking about this. One is the famous Berezinski-Koslitz-Thouless theory in 2 dimensions, and some other more recent work in 3 dimensions. We'll discuss Koslitz-Thouless in some detail if you've never understood it in detail earlier. From these pictures, it seems that the transition temperature should be determined not by the energy gap, but rather by the stiffness for phase fluctuations. Because after all, what randomizes the phase is, if the stiffness is small, it's very easy to randomize the phase. If the stiffness is large, then the phase does not want to get randomized. So that then raises the question, who wins, the BCS gap or the superfluid stiffness? And the answer, as we will see several slides down the road, is whichever is smaller, which makes perfect physical sense, because if you have an ordered state, whatever can destroy the order will destroy the order. You raise the temperature, if you first hit the gap scale, that kills you. Or if you first hit the superfluid stiffness scale, that kills you. Energy gap you've learned about in elementary classes. Stiffness, much less so. So let me say a few words about stiffness. So the superfluid stiffness is actually something that governs the free energy cost for fluctuations of the phase. In a uniform superconductor, the phase of the order parameter is actually spatially independent. So of course you pay no free energy cost. But if you try to distort the phase, then you get a cost which feels like the gradient of theta squared. And the stiffness tells you exactly what the value of the free energy cost is. So the reason why we use the word stiffness in this field is because it's the superconducting analog of the elastic modulus of a solid, right? If you try to distort the solid by putting in a strain field, then basically the free energy increase is by the elastic modulus here. Okay, and what are its experimental consequences? Because this is a very theoretical way of defining it. And let me tell you 2. The first is the London penetration depth is, I told you about the Meissner effect. If you put a magnetic field, so the unshaded region on the left is vacuum, shaded region is superconductor, the magnetic field decays to 0 in the bulk of the superconductor. The length scale over which it does that is called the London penetration depth. That's why the sub L. And the London penetration depth is exactly related to the superfluid stiffness. These are all universal constants. This is the permeability of free space in SI units. Okay. And the other manifestation of the superfluid stiffness, ds, is the following. If I look at the optical conductivity, which by that I simply mean the real part of the frequency-dependent conductivity, the one that leads to absorption of energy. Okay. Then in a superconductor, actually there's an energy gap. So there is no absorption at low energies. And then, of course, there's some absorption, and it could be much more complicated than what I've shown you. But because it's a superconductor, the DC conductivity must be infinite. And that DC conductivity actually is a delta function. Okay. Now you can say, how can I distinguish between a delta function and an infinite conductivity? The answer is there's a Kramers-Kronig. So there's an imaginary part. And the delta function will lead to a characteristic feature there, which can be measured in experiments and has been measured. So the strength of that delta function, the infinity is actually the superfluid stiffness again, up to universal factors. So it is the superfluid stiffness which is related to both the Meissner effect and, in a sense, to superconductivity. The fact that ds enters all of these three quantities is something that would require a whole lecture in its own right. So I'm not going there, but I'm just trying to give you a sense for why ds is important. So ds, the superfluid stiffness, controls all of these observable phenomena and more that I'm not talking about. Now, there is one terminology called the superfluid density, which is often used in the literature. So let me actually say what the relationship of that to the stiffness is, just so that those who might have heard of that will make a connection. So if I have electrons with a simple parabolic dispersion rather than some complicated band structure, k squared over 2m, then it turns out that the superfluid stiffness is just proportional to ns divided by m. Okay, where ns is often called the superfluid density. But more generally, the reason for not talking about superfluid density, but rather the stiffness itself, is that more generally, if one doesn't have a parabolic dispersion, one cannot separate the numerator from denominator and say there is a numerator which is a superfluid density and the denominator which is a mass. It is only this combination, ns over m effective, which enters ds, and therefore controls all the experiments and the phase stiffness that I talked about. That's why I'm talking about the superfluid stiffness rather than the superfluid density. Okay, now it seems like I've gone off at a tangent, but remember what I'd said earlier. I had said that gap determines Tc in a BCS superconductors, but the other possibility is that the stiffness might determine Tc. So let's discuss how the stiffness determines Tc by reviewing the Koslitz-Thouless-Berezinski theory in the next slide. Okay, and we will discuss 3D superconductors at the very end of the talk. So let me discuss the BKT transition in 2 dimensions, for which Koslitz and Thouless won half the Nobel Prize. The other half was given to Thouless and Haldane for the use of topology in quantum systems. Now, Berezinski passed away at a very young age, many, many decades ago. Had he been alive, he would surely have shared in the Nobel Prize of Koslitz and Thouless. So here is the idea. So here I'm drawing some configurations with arrows. Now, why an arrow in a plane? The reason is it's an arrow because, after all, I told you I have a complex number with a magnitude and a phase. So that's what it is. A complex number can be shown as a 2D vector. And I'm also looking at 2 dimensions. So every point in 2-dimensional space has an arrow associated with it. This is obviously a vortex configuration, and we are familiar with vortices by just looking at a sink and seeing how the water circulates there. But this is a superconducting vortex. And here I've shown an anti-vortex. So the vortex in 2D is a topological defect in the superconducting order parameter. And what Koslitz and Thouless said is that the Koslitz-Thouless phase transition of going from a superconducting state with an algebraic order, a sort of long-range order in these phases, to a completely phase-disordered state, which therefore has no superfluid density, no superconducting properties, is through the unbinding of vortex-anti-vortex pair. That is the content of their Nobel Prize. Okay, so inside the superconducting state, vortex-anti-vortex pairs are strongly bound, and as a result, basically long-range or algebraic orders technically persist. But when you hit the BKT transition temperature Tc in 2 dimensions, the vortex-anti-vortex pairs dissociate and completely disorder the sample. And now it's intuitively obvious that since it's the phase disordering which is responsible for this, Tc must be driven by the superfluid density. And there is a very famous result of Nelson and Koslitz that Tc is just given by the superfluid stiffness at Tc minus. So if you plot the superfluid stiffness versus temperature, then it decreases, and then right at the transition is the value of the superfluid density or stiffness that satisfies this condition. So the higher the superfluid stiffness, the higher the Tc. And actually, this was seen in measurements of helium-4 by Bishop and Reppe, and in 2D superconductors too. But I think probably the Bishop-Reppe experiment showing how they took various films with different values of the superfluid stiffness and showed the Tc scale with it exactly as predicted by Kosterlitz-Thouless theory was probably responsible for Kosterlitz-Thouless eventually winning the Nobel Prize, because this is the experimental demonstration of Kosterlitz-Thouless theory. Okay, now we have all the ingredients in place to talk about the work that my students and I have recently done and are still doing on upper bounds on the superconducting transition temperature. And let's just talk about 2D. So this is work done with 2 graduate students, Tamagno Hazra, who has just finished and moved to Rutgers as a postdoc, and Nishchal Varma, who is right in the middle of his PhD at Ohio State. And the paper is published in PRX, and quite a bit of what I will show you may well be unpublished as well. So are there any questions before we move to this? Navinder, are there any questions in chat, or do you have, or others have any questions?
No, there is no question. Yeah, but if possible, so maybe I would like to ask one question.
Please.
Yeah, so this is related to the upper limit of Tc.
Mm-hmm.
So there was an argument by Anderson and Cohen, so based on the divergence of the dielectric function, that they argued that the Tc cannot be more than 30 Kelvin roughly, or 30-40 Kelvin.
Yeah,
so
but
what was
so that argument is just completely wrong, because we know many.
Yes.
First of all, that was an argument based on electron-phonon coupling, making certain assumptions. Okay, and we know that there are magnesium diboride is an electron-phonon coupled superconductor. For that matter, this room temperature superconductor or these hydrogen sulfides and so on are all electron-phonon superconductors, which
they definitely break their bound.
Yeah, so that's some arguments. That's not really a bound in any serious sense. Right, so you should distrust such arguments totally.
Right. Okay. Yeah.
Yeah.
Thank you.
Okay. Okay. Other questions?
Please, if you have any question, you please write on the comments column. I will take them and then I will pass over to Professor Mohit.
Sure.
Or you can ask the questions at the end of the talk also.
Sure. Okay, so here is the intuitive idea of the bound, okay, that the transition temperature is related to the superfluid stiffness through the Kosterlitz-Thouless relation. And we will find a bound on the superfluid stiffness in terms of the optical spectral weight, and hence we will have a bound on the superconducting transition temperature. So the idea is the following. I already told you that the optical conductivity has a delta function peak at the origin, whose strength is the superfluid stiffness. So the total area under the optical spectral weight, so integral 0 plus to infinity, so the delta function is counted with half, the real part of sigma omega, including the delta function or half of it, is what is called the optical spectral weight d tilde. That's the definition. Okay. Whereas the area under the delta function is just ds. So of course, the total area, including the delta function, has to be larger than the delta function. So therefore, the optical spectral weight d tilde is an upper bound in ds. Now, this is a very hand-wavy argument. And since this is a very serious bound, let me take 2 seconds to sketch how this hand-wavy argument, which is physically very compelling, is actually derived rigorously. So I know this is not a seminar, it's a colloquium, but for one slide, since it's a real bound, please humor me and I will tell you. So we start with a general multi-band effective Hamiltonian, in which there is a kinetic energy with arbitrary band structure for multiple bands that are crossing the chemical potential, and we allow for arbitrary interaction energies. Okay. So what is the proviso? The proviso is that the external vector potential only couples to the kinetic energy through a pile substitution. This is the analog of P going to P minus EA, minimal subtraction, but for lattice systems. But the external vector potential doesn't couple to the interaction energy. This is certainly true for electron-phonon interactions. It's true for a wide range of electron-electron interactions, such as Hubbard superexchange, a lot of electron-boson interactions. It's true for the Feshbach resonance in cold atoms. Is it always true? And the answer is, if you have completely flat bands with no dispersion, or if you have bands with a certain kind of topological character, then this could fail. And actually, recently, we have generalized all the arguments that I'm about to present to you to those, but that would really take me into the realm of seminars. So let me not go there. This covers a very broad range of systems, okay? And then technically what we do is we say we want to compute the superfluid stiffness, and it's the linear response to a vector potential. We write down a Kubo formula and use the positivity of spectral functions to derive the bound, which I explained intuitively using some rules on the previous slide. So the superfluid stiffness is bounded by the optical spectral weight. And actually, in the process, we obtain a new general result for the optical spectral weight of an interacting system. And this is really details for an expert, but just telling you this is a result where for arbitrary dispersions and arbitrary interactions, we can figure out what d tilde is, this upper bound on the superfluid stiffness. And despite appearances, this quantity is much, much easier to estimate for various systems. So that's our rigorous bound, that KBTC, which is related by Koslitz-Thouless to the stiffness, is bounded above by the optical spectral weight. Now, the nice thing is it's an exact result, which is independent of pairing mechanism, which is independent of strength, doesn't make any mean field approximation. But it seems like a very formal result, and it's not at all clear that it's useful at all. So in the remainder of the talk, what I want to do is try and convince you that there are many situations where it is extremely useful. And we will see that this bound shines when you have low densities and narrow bands, and particularly when you have very strongly correlated material where the BCS-Eliashberg framework fails. Conversely, there are situations like aluminum or lead or so on, where BCS theory works extraordinarily beautifully. Our bound is valid because it's a general bound, but our bound will also be shown to be useless, meaning it will be humongously large. Okay? So these are lessons that we will learn as we proceed. So of course, a formal bound, it may be exact, is only as good as what you learn from it. So we have tested it against a wide variety of systems, experiments, quantum Monte Carlo simulations, model calculations, and I'm certainly not going to discuss the flat bands and topological flat bands, but let me try to give you a flavor for how this bound works. So as with anything, always look at the simplest case first. So how about looking at a parabolic band with a dispersion k squared over 2m, okay? And put in whatever interactions you want that lead to superconductivity and pairing. What results do we get? So we have a dispersion, we have a density of particles, we have a Fermi energy, and whatever interactions you want. So the first bound, that the superfluid stiffness is bounded by the optical spectral weight, just reduces to the statement in this particular case that the superfluid density is less than the total density, which is very natural. How can it not be, Okay. But it leads to a rather remarkable result, which was never discovered until our paper, that it also says that no matter what interactions you put for a parabolic dispersion, this superconducting transition temperature can never be larger than 1/8 the Fermi temperature. Now, the reason why this was never of any interest is because generally people were working with systems where the superconducting temperature was 3 or 4 orders less than the Fermi temperature. So why bother about 1/8? So the question is, are there places where we might test this, where the TC might actually approach 1/8? So originally, when we wrote this paper, we thought the only place where we can test for parabolic bands is the 2D BCS to BEC crossover in cold atoms. But it was extremely gratifying that a month ago, the Iwasa group actually tested our result in an experiment, and I will show you that experiment. Okay. So first, both of them deal with the BCS-BEC crossover, one in cold for atoms, but the other in the solid state. So let me describe what that story is. So this is a story of paired superfluidity in ultra-cold Fermi gases. So if you have very weak attractions, then as BCS showed you, you will get this, in quantum mechanics, a weak attraction leads to humongous bound states. So that's why you get these very large Cooper pairs that overlap in space. But if somehow you could get very strong attraction between your fermions, okay, and you can think of red and blue as up and down spins, or you can think of two species of fermions or whatever you wish, then basically you'll get non-overlapping pairs, which are just looking like diatomic molecules to the extent that you're thinking of atomic Fermi gases. And these diatomic molecules behave like bosons, and you should see a Bose-Einstein condensation of these molecules. Now, the fact that you can actually go from one limit to the other is because in the ultra-cold Fermi gases, you have this wonderful knob, the Feshbach resonant, that allows you to tune the attractive interactions in the lab at will. And actually, you can go through the entire BCS to BEC crossover. This is a beautiful field of ultra-cold atomic gases intersecting with many-body theory. And I can refer you to this short review article, which will show you a lot of the beautiful new results that have arisen in studying this BCS to BEC crossover, both experimentally, and there are just amazing experiments, and also theoretically. But coming back to the bound, which we want to talk about, actually in 2D ultra-cold Fermi gases, this bound can easily be tested, but these experiments have not yet been done. And you can also do quantum Monte Carlo simulations. And here, what I've shown you is we know what's happening in the BCS limit. We know what's happening in the BEC limit. You can think of the x-axis as increasing attractive interaction, very weak attractive interactions to the left, very strong attractive interactions to the right. You go from very large BCS pairs all the way to tightly bound point bosons with BEC. So of course, in the BCS limit, as you increase the attraction, TC goes up. But in the BEC limit, actually in 2 dimensions, there is no Bose-Einstein condensation. So if you go to non-interacting bosons, TC must go down to 0. But it's known from old work of Popov and Fischer and Hohenberg that the manner in which it goes down to 0 is very, very slowly. Only Russians could find a double log, right? And that's what Popov did. So actually, based on this, I've just drawn a blue interpolation, which just interpolates between these 2 limits. And we think that here, the bound should come, the actual answer should come close to the bound, but we have no way of knowing that it does or doesn't. It's a prediction. So we put our heads on the chopping block. But then, rather remarkably, December 10, 2020, appears this paper on the archive. This is from the Iwasa group. The details of the experiment are rather complicated because it's a rather complicated layered material, zirconium nitrochloride, and which they put in lithium intercalation. So there's a band insulator in which they are able to change the doping levels of lithium, which donates an electron to this 2D superconductor, and change the electron density by 2 orders of magnitude. You see, the thing is that you only need to change the interaction relative to the Fermi energy. So in cold atoms, for fixed density, you can change the interaction. In the solid state, there's no such knob. So what they did was, okay, we can't do anything about the attractive interactions of the system. We'll change the density by a huge amount, which is not easy to do in a metal. But they did it by doping a band insulator. And these are their data, the blue diamonds. And you can see that they basically approached the 2D bound of 0.125. And they actually approached the 2D bound of 0.125 in their TC. So which says that now there are systems where you can reach the 2D bound. So now let's look at non-parabolic band dispersions, because the parabolic band dispersion is very, very special. So you can, what to do? So the simplest thing you can do is to write down the simplest lattice model with nearest neighbor tight binding on a lattice with attraction, the attractive Hubbard model, okay, different from the usual Hubbard model, okay, which gives you S-wave superconductivity. And here you have the luxury of being able to do sign problem-free quantum Monte Carlo that I did with several Monte Carlo experts more than 10 years ago now. And here I'm plotting TC scaled in units of the hopping matrix element versus the interaction strength. Again, for weak interactions, you see a BCS, you expect a BCS transition. For strong interactions, you get tightly bound bosons, but their mass is very heavy because in order to hop, you must break and reconfigure. That's why TC goes like T squared over U. Here are the quantum Monte Carlo data, and here is the bound. So basically the bound, okay, so here you can't write down a simple analytical answer like 1/8 epsilon Fermi because this is not a parabolic dispersion. But clearly in the BCS regime of weak coupling, this 2D system has a TC which is hugely different from the actual TC. But the upper bound is a bound, but not a very useful one. But as you crank up the interaction, in fact, the BCS result just goes through the roof and has absolutely nothing to do with TC, which does that, okay, which the bound is able to capture. So in fact, the lesson of this is that, in fact, you might think if you do a good mean field theory, the actual TC might be the minimum. As I said, whoever kills you first will kill you, okay? And the bound is useful when mean field theory fails away from the BCS limit. The bound is useful in telling you what the maximum TCs you can get in a model. So then on to the real world. And again, I don't want to go into the details of the system. Here is a very strange superconductor, a single layer of iron selenide on strontium titanate. Reports range from 65 to 109 Kelvin. And here is a very nice review article. The reason why this is a very strange superconductor is if you make a bulk superconductor, its TC is only 10 Kelvin. But if you make a single monolayer, its TC goes up to 100 Kelvin. Okay, it's totally not understood. It's not even understood what the pairing mechanism is. So our kind of approach is really nice because we are agnostic about the pairing mechanism. We just take input from the electronic structure from RPES and we compute our upper bound and we get an answer which is 164 Kelvin. So it tells you that it doesn't tell you what the mechanism is, but it tells you that this is a very strongly correlated superconductor whose TC is about 50% less, okay, or perhaps even higher, depending on how you calculate, okay, from what is observed. So let me finally turn to twisted bilayer graphene. So this, as I told you, is this very new development where you twist two layers of graphene with respect to each other. You get very, very narrow bands. And in this very narrow band system, you get correlation-induced insulators at doping levels where band theory would have told you that there's a metal. And around those insulators, you get domes of superconductivity. Again, very little is understood about this system. What the pairing mechanism which gives rise to superconductivity, we don't know. Maybe it's phonons, maybe it's electron-electron interactions. Cases can be made for both of those arguments. Maybe it's both. But again, our bound doesn't care. We just need band structure. So the band structure is complicated here. You have 8 bands, 2 valleys, 2 layers, 2 spins. And the details of the non-interacting band structure, actually some details are still under debate. But here I use the Koshino-Fu tight binding fit to the continuum model of Bistrisker and McDonald. And then first I go through a rigorous set of inequalities, which I will not go into. Triangle inequalities, Cauchy-Schwarz, by introducing an inner product in the space of operators. And the rigorous answer is we say that TC cannot be more than 56 Kelvin, okay? Just based on band structure alone and nothing else, okay? Then we can say, okay, I don't want to be a mathematical physicist. I want to be a real physicist. So I can make some assumptions about what's going on. that the superconductive gap is very small and certain states are only impacted, and I can make a TC estimate of 15 Kelvin. And if I just use band theory to estimate this density matrix, which is here, actually I get a TC estimate. This I wouldn't call a real upper bound. The real upper bound was 50 Kelvin. I get a 6 Kelvin estimate. Okay, and the highest reported TC is 3 Kelvin right now in this system. So the TC bounds are very sensitive to band structure, but that's at least where we are. So I think we have a very serious case for understanding why the 2D materials will never cross a certain line on the TC-EF plot, because we have understood what sets the scale of that bound. The question is, why not repeat our success in 3 dimensions? And the answer is unfortunately not so promising right now. We don't know how to solve this problem. I don't just mean we, I certainly don't know, but no one in the field knows how to solve this problem. And what are the challenges? So let me discuss those challenges. Navinder, I will take about 5 minutes more. Is that okay?
Sure, sir. Sure, no problem.
Okay, so then we will end on time. So first is, by looking at this picture, a lot of experimentalists feel that the 3-dimensional Bose-Einstein condensation temperature is an upper bound on superconductivity. And this actually is just simply not true. And then let me discuss some issues of thermal and quantum phase fluctuations. So actually, this idea of what do repulsive interactions do to a dilute Bose gas, although the dilute Bose gas at 0 temperature was solved by Bogoliubov in 1944, until the 21st century, we did not know what the answer was. And finally, there's a rigorous result that repulsive interactions actually enhance the TC of a dilute Bose gas. So the BEC is not an upper, the non-interacting BEC is not an upper bound because it can be violated. And indeed, it is violated in this BCS-BEC crossover. Without going into it, I can just say that the best estimates of the peak in TC, although it's a very mild peak over and above the BEC limit, but it is known to be larger, both based on experiments and QMC. But theory really, it tells you that this answer, which is, by the way, the highest ratio of TC to epsilon Fermi known to mankind, is in the 3D BCS to BEC crossover of 0.22, quite different from the 0.125 that I was talking about in 2 dimensions, by the way. But we don't know how to derive this number in any analytical fashion or bound it in any analytical fashion. We just know it from quantum Monte Carlo simulations or experiments. And part of the reason why we don't know how to do it is because, unlike in 3 dimensions, the connection between TC and the superfluid stiffness is more complicated. Just on dimensional grounds, you know that there is a cutoff that must enter. And therefore, there is an open question of, given a certain cutoff, and there are natural cutoffs that Emery and Kibelson and others have discussed, A bar, how to find a upper bound on this non-universal prefactor. In Koslitz-Thouless theory, we had this wonderful thing that in 2 dimensions, there was no cutoff and the prefactor was universal. And so we could just bound it. Okay. Let me not belabor this point, but there is another question one can ask. Does TC have to scale linearly with DS in 3D? And the answer is, if you decrease TC enough near a quantum critical point, in fact, it does so in a nonlinear fashion, which is understood both from Josephson scaling theory and also from experiments. So actually, not that any one of us is really interested in how small TC can become. In fact, it can become 0 near this quantum critical point. But the manner in which TC and DS correlate with each other near quantum critical points as TC and DS both go to 0 is nonlinear, and they violate this linear scaling. So all of these issues say that the 3D case is really an open problem. So let me conclude. What I did was to explain the importance of trying to understand bounds and TC. And what we did was that in 2 dimensions, we could find a general bound. It was independent of strength of attraction. It was independent of mechanism. and we could bound TC by the optical spectral weight, which was simpler to estimate and to some extent dominated by band structure. For the parabolic case, this was a very simple answer, which anyone can remember. TC is less than 1/8 the Fermi temperature. And this, I believe, can be seen in the BCS-BEC crossover in cold atoms and has been seen in the BCS-BEC crossover in this ionic liquid gated material. It's a remarkable experiment. Okay, and for multi-band superconductors, where we do not have such a simple expression, but the top bound still holds, we have very useful TC bounds for systems where superconductivity is totally ill understood. Monolayer iron selenide and magic angle twisted bilayer graphene. And what we have learned is that these bounds are useful precisely where conventional BCS theory is not good. Okay, low densities, narrow bands, and strong correlations. So with that, thank you very much for your attention, and I'm very happy to take questions.
Yeah, so let's thank Professor Mohit for this very nice colloquium. So now this session is open for questions. So for questions, you can type your question in the comments box, and then from there I will take on, because this is not the way we generally you can ask the question. You have to type it, and then I can pass on the question. Yeah. So okay, in the meantime,
we are waiting for some questions. Can I?
Yes,
Hello?
Palam?
Yes. No, yeah, very wonderful, talk to, that we heard just now. I'm from a different background, but I'm curious to know a couple of things. When you said the high stiffness, ITC materials. So, are there, interactions or happening in the material sciences field and, to develop high stiffness kind of materials?
Yes. So this is a very interesting question, because what you would like to do is to have a large gap. So BCS says it's a high TC and also have a large stiffness. So you want to have the best of both worlds. And there are thoughts about how one might do that. Okay. Usually if one tries to have very large gaps, then the stiffness comes and kills you. That's the what I've been trying to show you. And so in multi-band systems, I think there are very good chances that you might be able to have some bands on which you have very strong attraction, which give you a large gap, but other bands of stiffness maybe you can have the best of both worlds. So these are design principles which I think one has to. But this is very early stages, so there's no progress along those lines. But you're absolutely right. What are the practical implications here?
Yeah. So, Professor Mohit, there is a question from Harish Gadvi. Okay. So the question is there a research on different material that limits Fermi temperature for the 2D material?
Okay, so the thing is, the Fermi temperature in any material, 2D or 3D, is generally very hard to change in metallic systems. Okay, because you can't change the electron density, therefore it's very hard to change. So the places where people have changed Fermi temperatures in 2D materials are ones which can be gated. Okay, because with gating, you can actually change the electron density. So you could see that, for instance, this material, this ionic liquid gated material, they could change. You can go and look at this. I seem to have some feedback.
No, I'm.
Okay. So please go and look at this reference, this archive reference, and you'll see that they've actually managed to change the Fermi temperature by 2 orders of magnitude. That's a remarkable change because of this ionic liquid gating. Okay. The other system in which you might be able to change the Fermi temperature by chemical doping are materials closely related to iron selenide. So there is very important work done by the group of Amit Kanigal at the Technion in Haifa. And you can look at his work on iron selenide telluride, where they have tried to go through the BCS-BEC crossover. And what they do is, again, trying to change the chemical potential is very hard in a metal density or chemical potential. But they looked at semi-metals. And in semi-metals, by doping, you can easily change. So these are very narrow gap semiconductors where the bands have suddenly overlapped and you get some conduction. So he has been able to also see experimentally the BCS-BEC crossover there. And in magic angle twisted bilayer graphene, again, by gating, people can change the carrier concentration.
Yeah. Okay. So there is another question by Varunshil PRL.
Yes.
So the question is, superconductivity has important potential for use in space exploration. Do you
Yes.
think scientists will be able to manipulate carbon lattice structure such that the electrons freely at lower pressures?
So these high pressure, these room temperature superconductors, actually carbon is a minor player there, but hydrogen is a very important player there. Okay. And the idea for making high transition temperature superconductors using hydrogen came from the work of Neil Ashcroft, a very famous condensed matter physicist whose book Ashcroft and Mermin many are familiar with. But he was actually thinking about an astrophysical problem. And he was thinking that if hydrogen under pressure becomes a metal, normally hydrogen, if you sufficiently cool hydrogen, it's a molecular solid, H2. But under pressure, actually, it metallizes rather than being a molecular solid insulator. And that metal actually becomes a superconductor. And Ashcroft and others thought that this might be relevant to what's happening on Jupiter. So from that idea came that, okay, let's take hydrogen because it has a very low mass, so it can have very high frequency oscillations. So the Debye prefactor in BCS theory can be very large. Okay. And so then people said, okay, hydrogen is very hard to deal with, so maybe do hydrogen sulfide and then try and put carbon in addition to hydrogen sulfide to make carbonated hydrogen sulfide. So really hydrogen is the real main player there in all those materials. And I do not think that those materials, there is any scope of having them superconduct at ordinary or ambient pressures. That doesn't mean that somebody won't find some other material that may be important for space exploration at ambient pressures.
Okay, so the next question is by Dheeraj Kumar Singh. So his question is, what properties of the element lets us select that for superconductivity experiments?
So the answer to that question is just simply not known, I'm afraid. So let's go to this slide. So I don't have a slide, which I wish I did, then I could have shown you that in the early days when people understood superconductivity in elements, they basically said that cubic systems are the best, three-dimensional systems are the best, avoid oxygen, and avoid magnetism. Those were the sort of rules of thumb that solid state chemists use. They were called Matthias's rule. Of course, the last rule was avoid theorists. And the jury is still out on whether that last rule is valid. But all of Matthias's other rules are completely wrong. Okay? Because if you look at the high temperature cuprates, they don't avoid oxygen. It's an essential element there. They are very close to magnetic Mott insulators. They don't avoid magnetism. They're not three-dimensional or cubic. They are tetragonal or orthorhombic materials which are layered. So every Matthiassen's rule is violated. Okay. So I'm afraid we just simply don't have such rules of thumb. Once people discover cuprates, then, sorry, let me just show this in full slide mode. So then once they discover cuprates, then they start looking in the copper age at copper oxides. Once they discovered it in iron selenides or iron chalcogenides, then they go along that path. But the first discovery is always just serendipitous. Of course, people have their insights, but those are like chemistry insights or solid state chemistry insights. Yeah.
Mhm.
So
Yeah.
that's the
So
best I can do.
yeah. So there is one more question from Hiranmaya Mishra. So the question is, does the Meissner mass depend upon the superconducting gap?
Okay, I'm not sure what you mean by the Meissner mass. So can you clarify, please? Did you mean the Meissner stiffness? Okay, we can wait for him to clarify.
Yeah. So maybe in the meantime we can take another question. That is a question from Kanksha Arora. This is a question little off our today's topic, but let
Okay.
us. I want a little insight on quantum computing has enhanced calculations.
So I don't think right now quantum computing has solved any practical problems of the kinds that we are talking about right now. It very well may in the future, because the way in which it could impact uh, science is that nature itself is a quantum computer. This is how Feynman actually wrote some of the earliest ideas of quantum computing. And one may be able to do a quantum simulation of a model, okay, in a much more efficient way on a quantum computer than one can do on a classical computer. But this is the medium to far future. This is not imminent. Okay. However, right now the feedback has been in the other direction, that understanding of materials and understanding of superconductivity has allowed people to make the hardware to realize a quantum computer, at least one platform for quantum computers, which is superconducting qubits, which is by no means the only one. I mean, there are trapped ion quantum computers and so on. There are issues of scalability. I mean, I don't know which technology will eventually be the best. Right now, the superconducting qubits are amongst the farthest ahead.
Yeah, okay. So there is a clarification has come from Hiranmaya Mishra. So
Okay.
he says that I mean photon mass in the medium.
Okay, so the photon mass in the medium is basically the London penetration depth, because that's the exponential decay in space. So the answer is, does it depend upon delta? So the answer is, the connection between it and delta is a little indirect. Okay, I'm tempted to say that if delta is 0, then ds is 0. But even that has to be said a little bit more carefully. There are things known as gapless superconductors. But ignoring such subtleties, it's certainly true that the presence of delta is required for ds. Within mean field theory, the relationship between the two is very tight. Okay, that the superfluid density or stiffness just scales like absolute value of delta squared. Okay, it's roughly speaking, delta is related to the condensate wave function. Absolute square of the condensate wave function gives you the superfluid density and hence the stiffness. But this relationship is very dangerous to use outside of mean field theory. Okay. For instance, the order parameter critical exponent and the superfluid density critical exponents at the phase transition are different. Or Costell's-Thouless theory is the biggest counter example to this, because here's a system in which there is a Meissner effect, and therefore there is a superfluid stiffness, but there is no long range order. So the long range order parameter goes to 0. So the relationship is very delicate. And I cannot say it in words, but mathematically we do understand what the relationship is.
Okay, so yeah, I hope that these answers are clear. So the thing is that now we are running out of time. See, already it is 11:57, and also it is must be very late at Professor
No,
Mohit's end.
that's fine.
So yeah, so we would
I'm
like to
wide
close.
awake, so if there are questions, I'm happy to answer them.
So yeah, please, you can if you have a question, you can send by email also.
Sure.
to Professor Mohit, you can send an email. That will be, I mean, you can communicate via email. So now I would like to hand over to our Dean, Professor Pallamaraju. So I'm handing over. Yeah.
So should I share
you.
my screen?
No, yeah, just wait. Thank you, Navinder. But I have also one more curious question,
Okay.
which is regarding this. Your theory of 1/8, of Fermi energy, and you said at that similar time, the Iwasa group was doing some experiments.
Yes.
So was it? I'm more curious. Was it kind of serendipitous, or it was, kind of discussed earlier, and then they will doing experiments and you'll bring theory? How was that?
So the thing is that I think they did not know about the 1/8 when they were doing their theory, but they have for long been ion gating superconductors, and they have for long been trying to see BCS-BEC crossovers. And the experiment is very beautiful. They measure the pair size by measuring the upper critical field and getting the coherence length. They measure delta by measuring tunneling spectroscopy. They measure the Fermi energy by measuring KF, or the density from the Hall effect. And they do density functional theory to look at the parabolic dispersion. So it's a very, very big research effort which has taken, they have been working on it for years. Okay. And their goal was to see the BCS-BEC crossover. And that's what their motivation was. And then they found a maximum TC, which was exactly what we predicted. And so, of course, they show that they've reached the maximum TC from that perspective.
Yeah. So that should have been very exciting time for you, because
Yes.
when where you're presenting, I could see that I was there trying to imagine that your whole group would have been excited to see that experimental result matching with your theory.
Very much so. Yes, very much so.
Good. Yeah.
So the paper will appear shortly in print, so you'll be able to see it.
Wonderful.
But it's on the archive if you want to see it.
Okay. I think I think that I'm not seeing also any other questions, but I think we had a wonderful talk, feast, in a sense, and of very exciting and top of the class research, and the results that you have presented, and in a lucid fashion. It's been very very informative and knowledgeable for us, and I'm sure several people who are deeply working in that field, and also the core we have high energy particle physics group also here in PRL. So I'm sure people will be pondering over applying more thoughts, and I'm sure they would be interacting with you, or looking at this particular aspect in their interpretations. And I really I would like to, on behalf of PRL, I would like to thank you very much, and also I'm sure some of your colleagues and students would have been joining, so I would like to thank them also, in the colleagues at the Ohio State University, for being with us in this particular interactions. And we would like to have this kind of interactions more in various aspects, and I would like to take this opportunity to thank you once again for taking time, and it's pretty late in the evening and night there for you. Thank you so much. I really appreciate it.
Thank you. Most welcome.
And continuing on with the PRL Colloquium series, I would also like to announce that we're looking at different aspects in the next week, which will be given by the Colloquium will be by Dr. M. Mahapatra, who's Director General of the Indian Meteorological Department, and he'll be talking to us on the weather forecasting in India, current status and future plans. So I think this we would also, I'll take this opportunity to invite and welcome you all to this another exciting talk, which I'm pretty sure that will be another exciting talk, just as we had it today. That will be on our usual time at 4 o'clock on next Wednesday. So please, mark your calendar and please join us. And thank you all. And bye-bye. Have a Take care. Thank you. Thank you, Professor Andrew.
Thank you. Bye.
Bye. Bye.